Okay, can you see my screen?
Yes, sir.
Okay, this is Kirtana. Um, Hiten, are you there?
Yeah, I'm here.
Okay, thank you. I'll go full screen. Okay, so any questions? This is the last time we introduced in a very, kind of formal way, the first order logic without the quantifiers, which I called as first order ground, first order logic without the fragment, without quantifiers. Okay, when you don't have quantifiers, you can treat these variables are as uninterpreted constants. And the key takeaway it was that the model, okay, first I described how formulas are constructed, and then the model here, because the variables are ranging over arbitrary domains, and the logic permits function symbols, terms that is expressions constructed out of function symbols and uh, various constants, and as well as predicates, in order to assign truth values to the formulas in first order logic. First, you need to assign meaning to those function symbols and predicates before you can actually start assigning truth assignments to atomic formulas and compound formulas in the logic. Therefore, the key takeaway is that the model consists of you have to assign, pick a domain to assign for the variables to range over, and an interpretation that assigns meaning to the function symbols. Besides, and if you had variables, of course you have to have an assignment given to those variables from the domain that you have. Okay. And so the general, so this then you can extend the notion of satisfiability and validity for formulas in first order logic by defining it the same way. Whether there exists a model that satisfies the formula, then it is satisfiable. If that it is for all models, a formula is considered to be valid if for all models. F is true for all structures. By the way, before I do that, today will be the last lecture on logic recap. Okay. And Thursday, since I have some commitment, there will not be any class. And I will send an announcement to this effect. And then from next week onwards, I'll be back in Chennai, and we'll have to pick a regular time, okay, to meet. And I will decide that because there are not many people. Hopefully, by that time, I'll have the registration deadline will be done, and in any case, we'll have to decide on a regular time for that, and that we will do over email. Okay, that's just a logistical thing. Okay, and then once you define satisfiability, and validity, you can define the dual notion of unsatisfiability as well. Okay, now this is general first order logic. Okay, now what you sometimes have is first order logic over theories of interest. That is also talked about. And there, when you have that, what you have is specific theories of interest. When you talk about first order logic, this way, then these M when you say something is valid, it has to be true. The formula has to be true for all possible domains and interpretations for the function symbols and so on. But if you're interested in proving first order formulas with specific theories, then where a theory means that you choose a particular domain and the operations and give specific interpretation to those things, then those specific domains with operations are what are called first order theories. I gave you examples of integers, reals, and there can be various other domains of interest as well. Then we call, and then when you combine that with the first order logic, the other part of it, then you call it first order logic with theories. And how is a theory presented? Once again, a set of constant, predicate, and function symbols. That's the syntactic part. And then you could present, define the thing by the particular theory by specifying, giving the models, explicitly giving the models to fix interpretation for the symbols in the signature of this theory. Or you can also view a theory as a set of axioms. It can be presented as a set of axioms, where axioms are actually first order, well formed first order formulas uh, over that signature. And you could say that, okay, any model that satisfies all the axioms, that is, that defines the theory, are the what we are interested in. Then so that, and then I defined what it means for a formula F to be satisfiable modulo T if and only if the formula is satisfiable for all the models that are of interest to you, as that defines those theories. Okay, and the formula F is said to be valid modulo T if and only if F is true in all those models that define the theories. Okay, and Z3 is a solver, that is, it is a decision procedure for deciding the satisfiable modulo theories. The theories means, I mean, whatever theories that it satisfies. Okay, um, and of course, if you want to, you can also use Z3 to prove formulas in first order logic, the general first order logic without theories, in which case you will have to define those function symbols and predicates as completely uninterpreted. Okay, otherwise you will have to specify those theories as types of the variables to be ranging over. I mean, you can use Z3 by saying, "Oh, I don't care what the type is," and it does allow you to do that. Okay, you can say X is of type some sort, arbitrary sort, which I don't give any particular interpretation as defined by a theory. So you can also do that. Okay, this distinction I want you to be I want you to understand. I think, is that any questions there? Okay. So, like I said, some common theories that are supported, that are of interest, usually for doing verification to modeling software and programming languages, software written in programming languages, are theories that correspond or that model the kinds of types that are used in programming languages. Okay, this kind, this goes from quite abstract theories to some specific theories. Okay, we'll talk about equality with uninterpreted functions. Okay, a theory that when only equality is defined is a theory, a first order logic with equality. You would have heard of first order logic with equality. So where only the equality between terms or expressions in that thing is defined, and all the rest of the functions are can be uninterpreted in the sense that they don't have any specific meaning, and that is called a first order logic with equality. And if you, yeah, that is the same thing as first order logic with uninterpreted functions, where the functions are just said, okay, they could be any functions and they only satisfied some logical properties that you normally attach to functions. Similarly, for equality, like commutativity, transitivity. So that kind is sometimes very useful to model software at a very high level, and you can prove properties about those things, or you can define theories that model things that are normally used in software, like fixed bit vectors, which are which is what our ints are in say in a language like C. You can have linear arithmetic over reals and integers. Here, I mean, when treating them as infinite precision, in a domain of infinite precision, real and integer numbers. You can have arrays, pointers, and so on. So, to give you an example of how you present a theory, I'll take the example of theory of equality with uninterpreted functions. Okay, now this is a very important theory because it's also quite useful in practice to model software at an abstract level, and that's why I want to illustrate this and make sure that you understand it. Here, the signature for the theory has these has function symbols, has equality as the only predicate in the theory, and a bunch of functions. Okay, inequality, and it has certain variables, and then function symbols, equality, I'm sorry, function symbols, and you can also have other predicates if you wish, like p and q and so on. But all these function symbols and predicates are uninterpreted. Okay, this is, they could be arbitrary functions and predicate, and equality is the standard equality. And then, okay, what does this mean? Okay, this means that the assumption is that the equality satisfies these three axioms. Okay, that it is reflexive, it is symmetric, and it is transitive. That's what these three axioms say. Okay, and the function symbols are uninterpreted, except that they should behave like functions. What does it mean to say that functions should behave like functions? Okay, these are two standard properties that you kind of assume, automatically, but these, here they're being defined explicitly. Okay, a function, okay, when if it is given arguments, set of here I'm showing you an NRE function. Okay, so it's saying that if a function is if they are applied to objects that are equal, they should return equal value, correct? And that's what this thing is saying. This is sometimes called congruence, a congruence property. All it says is, if a bunch of pairs of values are equal, x1 is equal to y1, x1 is equal to yn, then when you apply f to these x's, x1 through xn, and the value returned by that should be equal to what the value returned for equal. That is, if you apply the function for values that are equal, they should return the same thing. And since a predicate is just a special kind of function symbols that return Boolean values, true and false, the same thing should hold good for that. Okay. Now, this is a theory where you can then form conjunctions, a Boolean in a propositional combination of these kinds of propositional combinations involving equality and uninterpreted function symbols and predicates, and that is can be the theory of interest to you. Then what is the kind of formulas that you could that you will be able to verify? For example, okay, can you see this? Okay, this text thing that I'm showing, yeah. um, then you can make. So here is an example that I've highlighted in this theory. Okay, so this says equality. Here, equality I'm representing as double equal. Okay, and f is some arbitrary function. Then you can pose this kind of ask the question if this is satisfiable. Okay, can anyone answer, one of you, if this is satisfiable or not? So first, I want you to understand this is an instance of a formula in what I just now introduced, the theory of equality with uninterpreted functions. Okay, then you can ask if this is satisfiable. Okay, Kirtana, I don't know how many people are in the class today. Let me go to check that so that I'll know. Okay, there are only 3 people. Okay, then I'll take turns. Chinmay, can you? Oh, Chinmay is in the library, so she'll not be able to talk, I guess. So I'll excuse her. Hiten?
Uh, I do not think this is sad.
Yeah. Why is it not sat?
That it would violate the fourth axiom.
It violates what?
The fourth axiom.
Uh,
I, can you hear me?
Correct. Okay. See, yeah, it violates the congruence. Okay, if f of x is equal to if f of x is equal to x, certainly you can apply f to both sides, and they'll have to be not equal. Now, if I replace this, yes, okay, that is correct. Okay, and suppose I change this. Is this satisfiable? Kirtanam?
Yes, sir. Because f of x is x, so you have
Yeah.
f of x.
Okay.
So,
Yes. Okay. So you get the idea. So you can do a lot of things, and you can make certain really more complex. This is already quite expressive. That's the point that I'm making. Even though you are just saying, okay, it can be any functions, and the only thing it can has equality, you will see that you can use this simple theory to model, quite a lot of interesting artifacts and so on. And you can make formulas that are very complicated, whose satisfiability or validity is not so obvious. Now, here there were 2 examples that were very simple that you could clearly indicate whether they are true or not. So I'll give you an example, okay, of software where you can actually use that theory, which seems so simple that you can use to model. Okay, see, okay, and first I'll introduce the example and then I'll make the point. Okay, so here is, suppose you want to check a program equivalence of two programs. So here I'm choosing some very simple thing. So this computes, both of them compute square of an input y. Okay, I mean, here I'm just making a bunch of assignments, okay, after inputting y, but eventually then I assign y to z, and then I change y, and then I assign x to z, but effectively, when I compute x squared, when I return x squared, it is computing y, it is returning y squared. Here is a much more direct way of computing. Now, you may want to prove that these two things are equivalent. Okay. Now, then you could model this. I mean, if you type into CBMC, it'll generate formulas that model the first program and another formula that models the second program. Then you can check. Then it'll check. I mean, this is typically how this is modeled. Okay, the first one says, okay, introduce logical variables to denote, like I said, the value of each of these variables after every assignment. And that's what is being done with x0, y0, and z0 representing the initial value or the input value for the function. And then once you model this, whereas and R1 is the logical variable denoting the return variable, a return value. So this formula, which is from this theory, okay, of equality with this function. Now here star, this, if it's a C program, this would be a bit vector. Okay, so you may want to use one way is to use the theory of bit vectors, where star is actually multiplication operation over the bit vectors. And then similarly you can model R2, and then you can then say construct a formula which is unsatisfiable if and only if the programs are equivalent. Okay, so that's what I'm done here. I'm doing here. In CBMC, you would have asserted CBMC directly that R2 by inserting an assertion to R2 is equal to R1. What goes on inside CBMC is what produces these formulas. Okay, nonetheless, you can do this. Okay, and you can use the theory of bit vectors in Z3. Okay, and make all these variables that I've introduced here, the logical variables as ranging over bit vectors, and then do this. Okay. And then you will see that the SAT solver fails to, in this case, okay, if you can type this simple thing, and Z3 will take a long time, okay? And as you increase the size of the bit vectors for 32-bit integers, it may never, it'll take much longer than 5 minutes to actually return yes or no for this. Okay, this is true. I mean, you're convinced that this is true, isn't it? Do you have anybody have doubts that this is is not true?
Sir, are you asking about the statement
Yeah.
not being true?
Yeah.
Okay, but I just have a question. So we're coming up with the formula. So is this always possible? Like, I don't understand what
No,
the
no, no, no.
purpose of
I'm
it.
not addressing that question. Okay. Is it, you mean, how do I come up with these formulas? Is that's your question, correct?
Yeah.
Yeah. Now, let's suppose that, there is a way to systematically translate these programs into these formulas. Okay. So here we will start discussing that from next class as to how to different ways of modeling software behaviors using logical thing. But now, given that intuitively this models this, correct? Yeah. You can believe that
Mm-hmm.
because I'm introducing a logical variable to represent the value of the variables there as they change after every assignment, okay, which is what I'm representing here, okay. And then eventually R1 will take x1 squared, correct? Yep. Which is
Yeah.
the latest value of x after these assignments. Yep. And here, R2 is directly computed in terms of the initial value of I that is given as an input to function 2. So, so I'm just asking a rhetorical question that this should be true, correct? And which Z3, if you type this formulas, just for a moment, let's forget about how to get these formulas. Just let's take these formulas just in their own right. Then these are obviously equal. As a matter of fact, this one should be true no matter what star is. Correct. Okay. Here I'm
Yes.
giving star a specific interpretation as multiplication over 32-bit integers, which is what happens if you treat this as a C program. But what I'm claiming is, hey, look, this is just should be true regardless of what star is. Actually, it has to be true for any function. Correct? Because if equality takes the meaning of equality as I defined for the theory of equality with uninterpreted functions, and I leave star as uninterpreted, then this should still be unsatisfiable. Correct? Yeah, because this is something that does not depend on actual meaning that you give for interpretation that you give for star, or for that matter, any it doesn't it has to be true for any sort, okay, not just for integer, okay. Therefore this can also be then this can be modeled as, if I replace star with some uninterpreted function called mul for multiple multiplier, and then I say I don't know what the domain over which these variables are ranging could be any sort, okay. And multiplication is any function, uninterpreted function, except that it satisfies that congruence property, and equality satisfies these things, it should still be. And this is now in modeling this one as using this theory of equality with uninterpreted functions, okay. And you type this, okay, as a formula into this thing, and you will see that Z3 will prove this in a fraction of a second. Okay, so I mean the point is that you can use different theories, because indeed proving equality over equality formulas that involve multiplication over bit vectors, that is, the complexity is very high, okay, and as a matter of fact it's exponential, okay. And whereas this theory of equality with uninterpreted functions can be decided, the satisfiability, in polynomial time, okay. Therefore sometimes if it will be more practical to model, use these kinds of theories, I mean, with uninterpreted functions, if it suits you, the particular need at that time. Okay, so that is the point that I was trying to make. Is that clear?
Yes, sir.
Okay, Hiten.
Oh, yes. Yes.
Okay. Now, you see, for example, in this case, you can you can do that, but can you do that in all cases? No. Okay. Can you use the uninterpreted function abstraction? I call it abstraction because there I'm deliberately leaving what it means to do multiplication. But here this is this operator is an exclusive OR operator or fixed bit integer. Now here I'm doing some specific operations on bit vectors. Okay, so here the whether x squared after doing and expressing these things in terms of exclusive OR manipulation is equivalent to this very much depends on what exclusive OR is. So you may not be able to do it in all cases, that kind of an abstraction, okay, and then use uh, uh, theory of equality with uninterpreted functions. In this case, you have no choice but to use exclusive OR. If indeed, the program, in some cases, the behavior that you want to prove, in this case, the equivalence, is very much dependent on the fact that it's a bit vector. Then you cannot do it. Okay. I mean, the key takeaway here is that in some cases maybe you can use some for some parts of the program to represent using that leaving using abstraction. Other parts you can use bit vectors. Okay, so yeah, I mean I'm trying to give you motivate you the need, okay, that even theory with uninterpreted function with equality can be useful if you want to model things, program behavior in an abstract way. Now, theory of fixed with bit vectors has all these operations, okay, and then with equality, and you will yeah, and as I said, the satisfiability problem for here it is NP complete, okay, whereas an interpreted function with equality is polynomial, and that's the thing. And similarly, you can have a theory of linear integer and real arithmetic, which is decidable. And actually, on real arithmetic, in nonlinear real arithmetic is also decidable, and you see yeah, so you can then here the signature is this, and then you can have formulas constructed over variables ranging over this particular theory, and the satisfiability problem here is decidable. So polynomial for reals it is decidable in polynomial time. For integers, it's decidable. It's NP complete, and then so on. Yeah. Um, yeah. So here is an example. I mean, I'm just introducing these things, and this is a compiler optimization. Where will you need? Obviously, in some cases, you will need to use the complete real arithmetic. Okay, so here is an example of in compiler optimization, even arrays the selection and update operations on array are quite expensive. I mean, they are, expensive, and therefore compilers sometimes try to optimize to reduce the number of accesses to array. So here, a of j plus I, in array element at j plus I is being repeatedly updated to take the element of aj inside an array. So if j plus I, the index, the value of j plus I inside the array, oh, I'm sorry, the value j itself, j is here is some program variable that has been defined earlier. Since j is not being modified inside here, you could move this aj outside the loop and just fetch its value once and then use this. Now this seems like a fairly simple optimization, but is this optimization true? I mean, sound to do for all programs. So here is an application of compiler optimization. So this transformation and optimization, compiler optimization, is sound for every program only if the value of the array at j never varies, okay, forever in the loop. Now, this can then be, you can extract the condition that you want to check is a condition over integer arithmetic, okay. This optimization is sound if and only if this formula is unsatisfiable, which is saying that no, for all iterations of this for loop in which I varies from 1 to 10, it should be the case that j plus I should never be equal to j, because if j plus I is equal to j plus I is the value that at which it is linked, because if j plus I itself changes sometimes, then you can have this assignment. The value at aj can itself get changed, because if j plus I is equal to j, then you see what you're doing is aj is being changed. Aj is no more, the value of aj is no more a constant over all iterations. So you can kind of extract these kinds of conditions. This is an application for compiler optimization. And here you will need real integer arithmetic and theory of integers to be to model this kind of a thing. Similarly, you can have theory of arrays, okay, to model arrays and the specific operations of array that are of interest. So here, x, y, and z, and there's equality. These are ranging over arrays, and you have uh, read and write operations. And a theory of arrays is at least for where the index of the array, the size of the array, is bounded by certain number is here is decidable. Read is the select operation of array, and write is an update operation. They can be defined as in terms of these axioms. And then you can solve the equality, the theory of equality over arrays with these two operations is decidable under certain conditions. Okay. In general, this is undecidable. Okay. And but as long as you put certain restrictions, like I said, when the kind of formula that you restrict the kind of formulas that you're able to that you allow for deciding, it is decidable, although it is expensive, but still it can be automated. Okay, this can be used quite handy in a lot of software verification tools to model memories and so on. So Z3 supports some of these are some of the theories that it that it supports. Okay. And yeah, I mean, here I have and all these examples, this in this file I have modeled them using in smtlib format. And you can, here is the array example, and you can try them. Okay. And so on. So this was mainly to introduce you to some theories and how they can be used to model specific behaviors of programs, and then check them. Okay. Any questions before I'll spend some time in the half an hour I have to introduce you the quantifiers, okay, formulas in a full first order logic. Until now, I have not talked about quantifiers. Are there any questions about specific theories that I've talked about and satisfiability modulo theories and how they can be used to give and express interesting behavior and properties of programs? Yeah.
So on the previous slide, like where you did I plus j equals j, How exactly does that guarantee that J is not varying outside?
Yeah, I think what it does is the argument here is in this transformation is sound only if I've kind of replaced AJ inside the loop by a fixed value V, okay, which is computed outside the loop, correct? Hmm?
Mm-hmm.
So these two are equivalent. A sufficient condition to prove that these two are equivalent is that the value of J, of the value of J plus I, okay, when can this transformation be unsound? Okay, when if J at any point in the iteration itself changes, okay, or specific, yeah, J, the value of J, then it can be then AJ, the assignments, AJ, if it changes, then in any particular one, iteration, then it is this is no longer true. You cannot use the value of AJ computed prior to the entry of the loop. Okay. Now, when can this be violated? Where it is when J plus I, if J plus I, for some reason, the I value is varying in every iteration inside this for loop, correct? Yeah. So if at any point in the iteration J plus I will become equal to J, then you know that AJ is the value of assign. I mean, this will change because this is an assignment. If at any point J plus I becomes equal to J, then AJ gets changed. Okay, right? The value. Then it will no longer be constant. So this is like a sufficient condition
Is
to.
it the fact that I cannot be zero? So,
That is correct. That's
okay.
that's right. Yeah. So this is exactly saying, and the reason that this can never be true is because I can never be zero. Okay. So if you had I is equal to zero, okay, then this potentially this can be violated. Yeah. Yes.
Yes, sir.
Yes. Exactly right. Yeah. But I'm deriving this as a general condition. Okay, maybe there are other loops for which I could be varying. If I'm defining in terms of while, I can make here I is varying in a monotonic way. Okay, and the importance is that I should not be zero. Yeah. Okay. If it is zero, then AJ can be assigned with something else. Potentially. Okay, and so on. Yeah. If you have a while loop, then you know that, so this condition to derive when can this be non-varying, the value of AJ. And that itself is dependent on how the index values vary. And so deriving this condition is not so easy. Yeah. In this case, this is sufficient condition. And for the reason that you keenly caught, okay, expressed. Yeah. Which is that I, if it's I is equal to zero, then there can be some danger. Yeah.
Yes.
Okay. Yeah, so now let me introduce quantifiers. So for that, I will use, now this is a slide that I have, okay? This is, anyway, the slide that I use, the set of slides that I use to introduce first order logic without quantifiers, it's kind of, this is, there is more notation in this. And I think you need this extra notation to be able to introduce with full blown quantifiers and so on. I chose to use the other slide because I wanted to first introduce with as little symbols as possible. But once you start talking about quantifiers and so on, you will have to deal with a little bit more uh, uh, you know symbols and so on. So this has the same thing presented in a different way. Okay, so I'm defining the first order logic. You can see as with the syntax. Okay, and then it gives the semantics. You can go through. I will upload this also, and you can go through this set of slides as well. But the important thing is that look at the way that it specifies the semantics. This is in full blown detail. Okay, whereas there I used only for a fragment of the logic. First, it defines what, given a model, what does it mean to, it defines, starts by, let me see, okay. No. So the semantics, yeah. So first, like I did earlier also, I have to, S bar is to do a follow if it's, it's for each variable x. This is the assignment functions. Okay. Now, when you have quantifiers, you have to really deal with variables. Okay, you have to introduce variables and assignment to variables, like we did in propositional logic. Okay, and the quantifiers will have certain meaning. And so, in order to do that, you will have to introduce an assignment function, and that S bar is an assignment function, which assigns for every constant something, and some value from that domain, which is part of this model. That's what this thing is saying. And for every variable, it assigns some value, which is given by S. Now, S bar is kind of extended. S is a simple function which assigns assigns values to variable from the domains. S bar is extended to define meanings of function symbols and terms constructed over function symbols. So for constants, it assigns some element from the domain. If it is a variable, then it just picks the variable assignment function to define its value. And and for terms, it'll do things starting with constants. For any particular term, it first fetches the interpretation for that function symbol. First, it computes the value assigned to each of the terms, that is S bar applied to T1 through Tn, and then it computes the value using the interpretation provided for F, and that is the value for this term F applied to T1 through Tn. Okay, which is what I kind of did it formally there. This is just a different notation. Okay, now I'll start defining the semantics. All the rest are the same, except, and the way that I'm defining here is, since now formulas can have variables, therefore I need this. Okay, in order to define the truth value for first order logic with variables and quantifiers, then you need not only the model, because there can be variables in the formula. You need some specific assignment, okay, an assigning function, because if I have fx is equal to x or something like that, where x could be anything and f could be some specific interpretation, you cannot say whether fx is equal to x, because that may depend on the value of x and the interpretation given to f. So it may be true only for certain assignments to the variables, and it may not be true for the rest of the assignments. And that's why, in order to define the meaning of these formulas, not only do you need the model, which gives defines the domain and the meaning of f, but it has to, and it has to give particular assignment to the variables, and that's why um, this is defined in terms of a particular assignment. That is, if you have the variables, and that's what is being done here. Now, I'll draw your attention. These are all for usually the formulas without quantifiers. The rules shown here for 1 and 2. They assign truth values for first order formulas, which don't have quantifiers. Now, if you have quantifiers, then what does it mean? Let's suppose you have a quantified formula. Okay, this is saying when can phi is some formula that has variables that have defined over the variable x, and now you want to assign assign when that is true, given a model m, and some assignment to variables, because when you define in here, the formula phi can have some variables which are bound by this universally quantifiers, and some variables there, it can maybe y, which is kind of free in there. Okay, therefore here what you will have to do is, what it's saying is, if I extend the assignment s, okay, I mean the assignment function s, such that x is given some value d from the domain, and if x is x here, xd signifies the function which is same as s everywhere except for x, where it takes the value of d. Okay, this is kind of the formal way of saying this: for all x, phi is true given some assignment, if it is true for every possible assignment that I can give to x from the domain over which x is ranging. Okay, so DOM takes from the model the domain with that is associated with the variable x, and what this is saying is, if I change the assignment such that x is given the value of d, x value t, then it should be true. And this should be the case for every value, possible value of d from the domain. Okay, this is the kind of, you want to formally give the semantics of the thing, you need this extra thing in here. But intuitively, all this is saying is, look, for a formula like for all x phi, arbitrary formula is true if I replace x by some value from the domain D, okay, and then I replay every occurrence of x in this formula phi, I replace with value D, then then phi, such a phi in which I have eliminated the quantifier and replaced them with D, has to be true, has to be satisfiable. That is, it has to be satisfiable for every value of the domain in the domain D. Okay, this is a way of defining how exactly, and you can see why this is not so easy to you can check, especially when the domain is infinite. But this is how what you interpret for all x. Okay, now existential quantification is not defined, it can be defined formally. It is not shown here because existential quantification, there exists an x phi, is defined in first order logic as not of for all of x, not of phi. Okay, you can always define existential quantification in terms of for all, and that's why it is not shown here. And this is all that is one additional rule that you need besides showing the thing. Then the rest of it is the same. Okay, so in order to given that, and I'm assuming that that you have intuitively what for all we is. There are two corner cases which I want to bring to your attention. That's only for completeness. If the domain over which X is empty, okay, what is the meaning? Okay, so this for all X is always defined to be true. Okay, whereas there exists an X. Okay, there is this extreme case where the domain can be empty, in which case for all X is considered to be vacuously true. But when the domain over which X is ranging is empty, there exists an X is always considered to be false. Okay, because that's how it is in the extreme case. The meaning is defined. Okay, given that, now I want to go through a bunch of examples in the remaining time that I have. I'm already 7:30, so I'll take 5 extra minutes to pose these questions. Okay, so here you should interpret this turnstile here as logical consequence. Okay, and I've defined a logical consequence here. Okay. Yeah, so this says that something is and it's written this way: given a set of formulas, okay, that implies phi if for every model for which tau, okay, this is logical consequence. It says given a set of formulas tau that is said to logically imply phi, and that is written this way. Okay, if and only if for every model M that satisfy every axiom in tau for some variable assignment S, so does for every such model and a variable assignments in phi, the phi with that model. I mean, then phi should be true for that model. That's how logical equivalence is defined. Given that thing, now I ask you. I'll spend another 5 minutes with your. I'll indulge another 5 minutes for you to ask, if this is true or not. I'm going to go. I'm assuming that there are 3 people. I mean, since okay, I'll rotate through Kirtana and Hiten if you're still there. Okay, so is this true? So P can be any predicate. Okay, I'm asking if for all V1 P of V1 is true, is that is it's valid, will P of V2 be true?
Yes, sir. I think it should be true.
Yeah. Why?
Because it evaluates for like some domain element, then it has to hold for everything.
Correct. So since the meaning of for all means that for every possible value that you can assign to V1 from the domain, if PV is true, V2 is some specific value, no? So it is always that is satisfiable. Yeah, everyone believe that? Okay. And then full screen so that I can use. Yeah, true. Hiten, how about this? Is Hiten still there?
I not necessarily.
Yeah, why?
Well, because we only know one variable in the
Correct.
domain.
Okay, so there you cannot be sure. So this is a true. I mean, it's not true for all possible assignments. Yeah. Okay, that's exactly the case. Yeah. If if you know that this is true, once again, Kirtana.
It's true, I think.
Yeah, because for the same reason. Okay, so
Yes.
here I'm just saying, PV2 is true if it is true for any particular value. Here I'm expressing that in a formal way using existential quantification, right? And existential quantification is true if it is true for any one or more value of the thing. Now here Q is a binary relation, a predicate, binary predicate. Now it gets a little bit more complicated. What does this say? So if this is for that there exists an X, which for which there is always X is that X is related to every Y. Okay. Now I'm inversing. So does that mean there exists an X such that Y is related? There exists yeah. So first I'll ask if this is true. Okay, Kirtanam. Then I'll explain.
I think it's true.
Why?
If there exists some x, you can just take the same x with.
Yes. Okay. So for every Y, for every Y, there exists an X. So here you're saying for every X, for every Y, obviously there exists an X. Okay. Whereas the reverse of it is not true. Okay. Yeah. Because this is insisting, okay, this one is insisting there must be, that there may be a unique y, for every x. Whereas here it's saying, for every x there exists some y, but they can be different. Yeah. Whereas the right one is insisting that there must be unique y. Okay, that every x is related to under q. Okay, so it gets tricky. So similarly, this one, okay, this one I'll end it with this um, thing. So this is a little bit more complicated. Hiten, can you take a crack?
I'm not sure, but maybe false.
Yeah, why are you taking? Is that a wild guess, or you? Uh,
No, no. I mean, I don't think there should be. I
yeah,
don't.
what is it saying? So this should be valid, is what it's saying, correct? So this is
Yes.
the notation. First, I want to clear the notation. Okay.
So, like, what I understand is that there is an X, which being valid implies that every other variable is also valid for P.
Correct.
But I don't know if a variable like that can exist.
Yeah, I see. This is actually true. Okay, and you can see why it is true. See, either see this is saying, see P. It actually depends on a P. Okay, so here P is left uninterpreted. Okay, you should. When I say PQ here, they are this this P could be any predicate. Okay, suppose P, there are two cases to consider. Suppose the predicate P, there are some values in the domain. For some values of x's, P could be false. Okay, or P could be, a P might be defined, I mean, yeah, it can be, yeah. So if it is P is false for some domain, okay, then see this, there exists an X is ranging over this entire thing, okay? So if P is false for some of the thing, if it is false, okay, and even if it is false for everything, then this P of X itself will be zero, since logical implication is vacuously true whenever the antecedent is true, whenever the antecedent is false, even if P is, there's no X for which P is true, okay? P is true, then this entire formula will become true, correct? Yeah. Now, the other case is when P is true for every element, okay? Then in which case this will always be true. Yeah. If those are the two possible cases for P. In either case, if P is true for every element in the domain, then by virtue of this will be true. Okay, the moment the consequent is true in an implication, this will reduce to true. Okay, yeah, and therefore there exists an X true is always true. If there are some values for which P is false, then also this will become true, correct? For the rest of them anyway, if P is true for some value, whenever that thing is if it is so that those are the only two cases. Okay, if P is not true even for one or more elements, this will implication will reduce to false, I mean to vacuously to true, and therefore it doesn't matter. In the other case, the consequent will be true, and that's why that is true. Now I will leave these two things since it is getting late. I will upload this, and you think about these models. I mean, all these things you can type into Z3 with quantifiers. These are a little bit of a brain twister that I'm modeling, and I'll show it next time how quantifiers can actually be used to compactly model certain behaviors, and so therefore that's why they really serve real purpose in practice. Although satisfiability using quantifiers is super exponential. Okay, it's p-space complete. And so it is not very practical to do, but if you have a certain bounded number of quantifiers, you can still manage. And Z3 it does allow. It does implement decision procedure for checking formulas with quantifiers. So I will leave it and we'll discuss this. I'll let you think about why, understand why indeed these things are, some of this are true and some of this is false. And there'll be some cases where it can be, it can be false. Okay. And, so I'll leave it there, and I will continue this discussion with some Z3 demos of formulas with quantifiers and uninterpreted functions next time to complete. Okay, so I will adjourn the class here unless you have some questions. Okay. Thank you.
Thank you, sir.